So my name is Johannes Lotz, and I will continue looking at AD and AAD from a different angle. I want to present a selection of breakthroughs from my point of view, which were required to bring AD from research to industry. And as Luca already said, the first AD research is more than 50 years old. I myself started in research at the RWTH in Aachen in the group of Uwe Naumann, and moved a couple of years ago to Numerical Algorithms group, NAG, and now I'm the technical lead there for the AD team. You can ask questions in the chat as announced, and I will try to make time at the end to answer those if there are any. For everything I talk about today, sources can be looked up easily on the internet, so I don't claim anything to be my original contribution here, so I skipped the references. If you have any questions where things come from, just write me an email and I'll let you know references. All right, so I will be a little more specific looking at AD in C++. So automatic differentiation in C++ is widely adopted in quantitative finance. That is a claim from our perspective. That's the observation. So C++ seems to be a language which many banks choose to implement their quantitative finance libraries. As Luca already pointed out, computing sensitivities is suitable or important in various points. For example, computing risk, but also when doing the calibration, then you also need derivatives of the function you're calibrating. Automatic differentiation, I give a very brief introduction because Luca already gave the introduction. So conceptually it is, so there are three ways of computing sensitivities or derivatives of a computer program. The first one would be bumping or finite differences. That means for each input individually, you change the input and you observe the output, the change in the output. The second option is to, with pen and paper, derive from the original problem formulation, the sensitivity equations, and implement a second program. That would be completely a symbolic pen and paper work plus two implementations, one for the original, one for the sensitivity equation. And the third one is AD. I refer to it as automatic differentiation, but I will come back to that word later. So AD is a semantic transformation to the program. There are pros and cons which method to use. If you're interested in more details regarding that, drop me a message or have a look onto our website. So I want to look at a couple of breakthroughs, which in my opinion led to the success of AD in C++. Those are, in that case, three aspects. So the programming language itself, which enables AD, research or algorithmic insights, which made it over time into the tools, and also applicability and maintainability, which are required for having a sustainable solution in the end for production-sized codes. In addition, at the end, I will have one slide about what's coming. What do I think? So that's a personal view. What do I think is important in the future, and what we could or will see to come from research into industry in the area of AD. And I will also present what the AD solution looks like at NAG. All right. So C++ is a feature-rich, modern, and efficient language, and it's supported by matured tool chains. I also know that C++ is a complicated language and that the amount of people which are capable of writing maintainable C++ code is not very huge. But overall, it seems that the advantages outweigh the disadvantages. So many banks decide to use C++. AD in C++ can be implemented using the typing system or by overloading. And the nice thing about that is that it's embedded into the language and that it's so it's almost the full language coverage out of the box. I say almost because there are very specific elements, ternary operator, for example, which pose some challenges, but it is almost the full language coverage. It is straightforward to apply, and well-known types of compilation errors occur. So straightforward to apply. With that, I mean that everyone who learns C++ also learns what overloading means. That means that the method is not very difficult to understand. Well-known types of compilation errors, though compilation errors are sometimes hard to read, they are at least well-defined in C++, so there is no surprise on that side. Templates and inlining in the C++ language combined with the compiler optimizations gives us quite a good efficiency. It is very interesting that the compilers, so with template expressions, I come to that later, compilers are capable of producing very short assembly code for local statement gradients, but I come to that later. In C++, there is a strong tooling support. Since it is a complicated language and evolves quite quickly, also for refactoring, people came up with a very good tooling for the language, so Clang lib tooling, and that can also be used for help with activating the original code. And also clearing out stumbling blocks, for example, as I mentioned, the ternary operators, a tool can be used, so Clang tool can be used to fix all of those small problems. From my point of view, the outstanding features in C++, so of course, operator overloading and templates, auto-type deduction and lambda captures are also two very important features. Auto-type deduction makes it possible to extend the statement level pre-accumulation template expressions. I'll explain in a little more detail later, to extend that to basic blocks. And lambda captures, so Luca mentioned the PDEs. When you have time iterations, usually also checkpointing is required. And for checkpointing, lambda captures are can very nicely be used because that conceptually automatically writes a checkpoint. And that is a language feature, which is a great thing to have. In summary, from my point of view, C++ is well suited for the application of AD. All right, next is the algorithmic side, algorithmic insights into AD. AD is researched actively for decades. Most useful insights made their way into the tools. In AD, since many decades, there is a every 4 years a bigger conference. There is every year at least one, sometimes two smaller workshops. So it's a pretty active community overall. And since I would say 10 to 20 years, there is more and more overlap with machine learning. And that also shapes the direction of AD, just because it's such a big field. And I want to go through 4 important aspects which came from research and made it into the tools. The first one Luca already pointed out very correctly, and that is what I can't stress enough. So the biggest asset of AD is AAD, so reverse mode of AD, or AAD stands for adjoint AD. That's exactly the same as backpropagation in machine learning, therefore also the overlap. And with AAD, there is a reduction of 1 order of complexity in computing the sensitivities, which means instead of computing, so depending on the number of parameters, etc., instead of computing something in a couple of years, you can actually compute it in a couple of seconds or minutes. So in the beginning, when I learned about AAD, and also when I teach it to students, in the beginning, it feels a little bit like that can't be true. Then you see the examples, and you actually see, okay, so the reduction of complexity works. Then it feels a little bit like magic. And when you start understanding it, then you see, oh, it's actually an algorithmic trick, data flow trick. And when you continue a little more, you see also parallels to the adjoint equations for PDEs, for example. So there is a lot hidden, but it's, in my view, a very beautiful technique. AD is, so Luca also already showed graphs. So conceptually, AD can be completely expressed in graph algorithms. And a lot of research in AD is on graph theory and forward and reverse mode and everything in between. So there are arbitrary many modes conceptually, is defined by the ordering of eliminating nodes or edges in a graph. There is a lot of research to find the optimal ordering for this elimination technique that is NP complete. But luckily, there are a couple of very straightforward elimination ordering approaches, which can be implemented in C++ and with template expressions quite nicely. That is the pre-accumulation. And unfortunately, the picture is a little blurry here. So on the left is the original tree, which represents an expression. So at the bottom is the output, at the top two inputs. And with statement level pre-accumulation, we remove the two nodes in the middle, and we only store the graph on the right, which makes not only saves memory, but also makes the adjoint faster. This technique can not only be applied to statement, since we have auto type deduction in C++ and C++11, we can also extend that to basic blocks. Pathwise adjoints. Luca showed the approach as well. That is also a very important step to fight the main enemy, which is the memory consumption for the adjoint AD. So tangent AD, memory consumption is not a problem. For adjoint AD, memory consumption might be a problem. And pathwise adjoints exploit a specific structure in a code, which is a specific data flow dependency. And if that exists, then you can reuse parts of the tape memory. You can override that without losing any information. That is a general technique whenever this data dependency exists in the code, for example, also with ray tracing algorithms. But with that, the memory consumption problem is mainly resolved in Monte Carlo codes. Not fully, so still in each individual path, there is a time iteration potentially, et cetera, et cetera. So there is a lot of tape to be written, but there are other techniques like checkpointing, for example, to reduce that. And Luca also already mentioned the implicit function theorem. When there is a nonlinear solver and given a solution, then the linear sensitivity equation to that nonlinear function can be solved with a one linear solve step. But there is also another approach, which is a little less known and in my view also a beautiful idea, reverse accumulation. That actually only requires the adjoint evaluation of the last iteration step of the fixed point iteration. And then it uses this adjoint and iterates on that until convergence of the adjoint values. Not as widely used. In some circumstances, it brings more robustness. In others, it brings more accuracy, depending on how near you are to the actual solution. But that's another approach. And I forgot one point in this list, which I wanted to mention as well, which is checkpointing. That's also a very generic technique, which is incredibly useful. And there is a theoretical optimum for checkpointing in a time iteration. And that's the only point where I want to mention a name. So in that research, Andreas Grivank was involved, and I wanted to honor him here explicitly. And that can be used to almost arbitrarily reduce the memory consumption in a time iteration. And yes, summary here, AD research got incorporated into the tools. All right, next point, applicability and maintainability. So I think vital for the adoption of a technology is ease of use, support, and tool chains. AD tools matured over times, so they have been applied to many codes. A huge amount of small obstacles have been removed, bug fixes implemented, important features implemented, etc. The level of abstraction raised here and there for relieving the users from acquiring too much AD knowledge. I think there is still a good path to go, but that's what I envisage. From our perspective, support is always very important once it comes to production codes. And compiler toolchains also got better over time. So everyone knows that once we update the compiler, we might get different numbers or even compilation errors, etc. But in my experience, the compilers on different systems get luckily better and better. And the last point here is that working with many codes, specific design patterns reappear again and again, and recognizing those and using adjoint code design patterns in combination with a tool which supports them makes code nicely maintainable. So again, from my point of view, sustainability and AD go hand in hand. All right, what comes next? What carries potential to find its way into industry? I've collected a couple of points here. So I think architecture agnostic solutions will come. So as we've heard, different hardware will always be used, presumably. So CPU, GPU, or other evolving hardwares. Here I want to briefly talk about algorithmic and automatic again. So algorithmic differentiation refers to the fact that we use the algorithm that we derive or compute sensitivities of a given algorithm line by line. Automatic differentiation refers to the fact that we don't have to do that ourselves, but a tool does it for us. Unfortunately, it's not fully automatic at the moment, and that's already a sentence we hear for many, many years. But I still think that is achievable, and we're getting closer and closer. Of course, always further reduction of runtime and memory consumption. So the more research happens, the more we can also integrate that into tools. And I also hope for more libraries to support AD versions by default. That can be, so for the DAG library, we provide those, but also that could be Boost, BLAS, LAPACK, the standard library, maybe even AD in the C++ standard, all of those things. And yes, I think collaboration between academia and industry is very important and should be continued. All right, so very briefly about the tools at NAG. So the main tool is DCO C++, derivative code by overloading. We've helped major investment banks over the last 10 years to go to AD. It improves risk management, and yes, we implement various features in the tool. We regularly update the tool, and it computes accurate first and higher order, so second order or arbitrary higher order sensitivities, and depending on the number of parameters and the underlying code, up to 36,000 times faster. All right, and with that, I want to wrap up. Thank you for your interest, and I want to introduce now Mariam Akram as the next speaker.